Well, I hope everyone had a good break. We need to keep going, though. All right, we need to keep moving. I don't have the average for the test. I don't recall what it was. I believe after the curve it is up above a 70. I want to say that before the curve the average was like a 68, and after the curve it was obviously 7 more than that. If you have any questions on the test, please just get with me. As usual, we can go through it. If you feel like you don't understand what went wrong or you think you deserve credit when I took off, just come sit down with me. We are going to pick up exactly where we left off, and I had forgotten where we left off, so I went back and I watched my YouTube lecture, at least the last 10 minutes from last time before the test, and we were doing Lagrange multipliers. So I don't know if you're going to be able to clear the cobwebs out of spring break, but the last problem I did was a problem that I had offered as bonus that I believe 1 or 2 students turned in, and then I did that problem using Lagrange multipliers, and it was much easier. And so today what I'm going to do is just remind you of what Lagrange multipliers method was, and then I'm going to do one more example, and then I'm going to move on to the next section. All right? Actually, do one more example and then show you one more thing after that. So with the Lagrange method of Lagrange multipliers, it gives us a way of finding the maximum and minimum values of a function of either 2 variables or 3 variables when that function is constrained to some equation. And this method actually extends out. You can go further than a function of 3 variables. You can go to a function of 4 variables, 5 variables. That's what makes it so powerful. And then, as you'll see at the end, you can have more than one constraint also. So where I'm going to pick up is when we have a function of 3 variables, how it is that we can find the maximum or minimum. So what we do is we take the gradient of the function we're trying to find the maximum and minimum of, and we set it equal to lambda, which is some constant, times the gradient of g, where g is the constraint equation solved, like you get the constant on one side. I think I can go back one more slide and show you this. There we go. So if you have a function of 3 variables subject to a constraint, g of x, y, z is equal to a constant, then what you do is you find the x, the y, the z, and the lambda that make the gradients equal to each other, or parallel, so they're off by a constant. And you also have to satisfy the constraint equation. That's it. If you can find those values, that'll tell you where the max and mins occur. So I thought the good example to start would be to do a word problem. And I'm going to do this one right here. So you have, the question is find the point or points on the sphere x squared plus y squared plus z squared equals 4 that are closest and farthest from this point. So you have a sphere, right? And you have a point sitting out in space. Let me take those points out of there. So there's a sphere and there's a point. So, you know, Earth and a satellite, Earth and a meteor, whatever, doesn't matter, right? Earth and something. You want to know where on Earth, what point on the surface of Earth is closest to this point and which one is maybe furthest away. So does it make sense to you that the point closest is right here in the blue? The one furthest away would be on the other side, correct? In red? Okay, so we would like to find those 2 points, if possible. Somehow this is a Lagrange problem. So let's see if you can help me get it set up. What is your objective function? What is the function you're trying to find the maximum or minimum of? Is that it? Is this your f? Read the problem. Find the point or points on the sphere that are closest and farthest. So you're talking about 2 points in space, right? This one and some other point, right? And you want to know a distance between those, don't you? You want to know when that distance is the smallest and the largest. But see that this point's fixed, right? That point's fixed. The other point can't just be anywhere. Where does it have to be? On the sphere. So the sphere is the actual constraint of that other point. Understand that? So that's actually the constraint equation. The objective function, which is the one we're trying to find the max and min of, we have to come up with, which would be the distance between 2 points. So what is the distance between 2 points? What is the distance between, let's say, a point, let's call it x, y, z, and that point right there, 3, 1, negative 1. So what is the distance formula? I always press the wrong button. What is the distance formula for points in three-dimensional space? You could do a vector. You could, yes. But then if you do that, well, I guess we could. We could do that, yeah. You want to do that?
If we find the length of it.
If that's the first thing you're thinking, then I'm willing to go with that. I was going to go just straight to a distance formula, but if that makes most sense to you,
look at it, that's the same thing.
it's the same thing, exactly. So let's call it d for now. The distance should be equal to the square root of because it's a length of the vector that connects these points together, right? So the vector that, let's say, connects this point to this point, wouldn't that be this coordinate minus this coordinate? Squared plus this coordinate minus this coordinate squared plus this coordinate minus this coordinate, which would be z plus 1 squared. Do you agree that that represents the distance between x, y, z and 3, 1, negative 1? Yes? Any questions on that? We want to know when that's the biggest it can be and when it's the smallest it can be. But we have to be able to live on that sphere, right? So I'm going to convert this d over to a function of 3 variables, because that's what it is, right? Distance relies on x, y, and z. So it is a function of 3 variables. Here it is. That's my objective function. What is the constraint equation? So constraint, the book uses a semicolon to, when you're doing your homework, they say here's the objective function, and then they put the constraint next to it. So like this. Okay, so that's our constraint. Then the left side of this is our g of x, y, z. Follow? Now what we need is to find an x, a y, a z, and a lambda that make this true and make the gradient of this a scalar multiple of the gradient of this. So how many equations am I actually going to have here? 4. It'll be 3 from the gradient, and then a 4th one is this one. So let's write down these 4 equations. The first equation is going to be the partial of f with respect to x must equal lambda partial of g with respect to x. I realize you had spring break, but I am expecting that you are picking up where you left off. Okay, if you have to go back and watch a little bit of the last lecture, go ahead. That's where I'm picking up. It's as if we never left. Partial of f with respect to y equals lambda partial of g with respect to y is the second equation. The third equation is the partial of f with respect to z must be equal to lambda times the partial of g with respect to z. And then the fourth and final equation is going to be the constraint equation itself, which is x squared plus y squared plus z squared equals 4. Those are the 4 equations we have to satisfy. Any questions? We're good? Okay, let's take the partial the partial of f with respect to x. Now that looks bad, but it's just chain rule, right? So we're going to treat y and z like they're constants. What is the derivative of the square root of something? 1 over 2 times the square root of that something, right? So I'm going to have to erase some stuff if I'm going to keep this all on camera. So why don't I erase this? Don't think I'm going to need that right now. So I'm going to do equation 1. If you're doing it on your paper, just work it below. But equation 1 is now going to turn into, okay, this is, we said 1 over 2 square root of all that stuff, right? Which I'm going to call junk, times, I use junk, I'm paying tribute to my old professor. He used to always do that too. He used to always just write junk. And so I'm doing junk too. All right. Now, that's a derivative of the square root of something then, times derivative of what's inside with respect to x. So these are gone, aren't they? Who cares about those? This, though, another little chain rule. 2 pops out, right? 2 times x minus 3 to the first power. First power, I don't need to write it, times the derivative of what's inside, which is just 1. So that's it. That's a derivative of f with respect to x. That must equal lambda times the derivative of g with respect to x. Now here's g. What's the derivative of g with respect to x? 2x. All right, that wasn't so bad, I guess. We okay with that? All right, now, second equation. Take derivative of this with respect to y. So I still get 1 over 2 root junk, right? Times, now go inside, derivative of the inside with respect to y would be 2 times y minus 1. Is that correct? Agree? Yes? Okay, you're looking like, yes? Equals, right? Lambda times 2y. Third equation. 1 over 2 root junk times 2 times z plus 1 must equal lambda times 2z. And then the fourth equation, remember, is this one, right? Let's just not forget that's our fourth equation. All right. Any questions before I continue? No? Okay, what I'm going to do, and this is where you're going to run into the issues when you're trying these on your own, is, how are you going to go about solving these, trying to figure out what x, y, z, and lambda are. I'm going to solve each of these for lambda, and then I can set them equal to each other, can't I? Do you agree with that? So if I'm going to solve this equation for lambda, I'm going to have to divide by 2x. What do I have to promise you then? X can't be 0, right? If I decide to solve this for lambda, I have to divide by 2y, which means I have to promise you that y can't be 0, right? And if I do the same here, I have to promise you that z can't be 0. So as long as I assure you that x, y, and z are all not 0, so I'm going to say that, suppose x, comma, y, comma, z, all of them are not 0. So x and y and z are all not 0. Then what does equation 1 turn into? By the way, these 2's canceled, didn't they? Those 2's canceled. Those 2's canceled. So what does this turn into if I solve it for lambda here? X over 3 on the left side over 2x in the square root of the junk, right? So I'm going to put 2x root. I'm even going to get shorter. I'm just going to root j instead of root junk, okay? That's lambda, isn't it? That's lambda. I'm not going to write lambda. What I'm going to write instead is, well, I'll write lambda, okay, fine. Let's go second equation. What does the second equation become? Same thing, divide through. You get y minus 1 over what? 2y root j is lambda. And the next thing, third equation, is z plus 1 over 2z root j equals lambda. Now, what am I allowed to do at this point? Set them equal to each other, right? So why don't I set, I'm still working here, why don't I set 1 equal to 2? Okay? If I set 1 equal to 2, I get x minus 3 over 2x root junk must equal y minus 1 over 2y root junk. Now, I don't like the root junk. May I multiply both sides by root junk? Yes, right? How can you assure me that the root of the junk will never be 0? Because remember, you can never multiply both sides of an equation by 0. What does the root of the junk represent? Go back to where it came from. What does it represent? It's the distance between x, y, z and that point, right? Can that distance ever be 0? Not if we're on the sphere, right? Unless that point lives on the sphere. But I don't think it does. So we're safe to multiply both sides by root junk here. And we can multiply by 2, couldn't we? So it's going to look a little nicer right now if I just go to this. Right? Now, can I multiply both sides by x? Is x ever going to be 0? Not right now, right? Not right now. So I can multiply both sides by x. I can also multiply both sides by y, can't I? All right, so let's do that. I'm going to continue working. I guess I'll just work right in here. Okay, I'm continuing this. Multiply this side by y, you get xy minus 3y equals. Multiply both sides by x. X goes away here. You get xy minus x. You see how nice this is about to be? Subtract xy on both sides. And you get that, what, 3y is x? That's a relationship between x and y now, isn't it? Now, that was me just solving one of the, setting just 2 of those equations equal to each other. What if I go and I set the first equation equal to the third equation now? I'm probably going to get another relationship, right? So you want to go ahead and do that? Any questions on this? Seeing some glazed looks. That could just be spring break still. Okay, what if I set equation 1 to 3 now? Then, yeah, it should get a relationship x and z. Let's see. That's equation 1, right? That's this. Now, the third one I erased. But it was z plus 1 over 2z root junk, wasn't it? Do the exact same thing we just did. Multiply both sides by root junk, multiply both sides by 2, multiply both sides by x, multiply both sides by z. You should get xz minus 3z equals xz plus x. Y'all understand what I'm doing there? Okay, xz's cancel. You get negative 3z equals x. Now I have a relationship between x and z, don't I? Let's get one more relationship. Well, maybe we don't even need it. Let's see. I don't think I need it, because what's my fourth equation? The constraint, right, which has x, y, and z in it. So I'm going to go ahead and write my constraint down right here. Equation 4. With equation 4, I have x squared plus y squared plus z squared equals 4. Now, I know if I leave x alone, I know I can just say x squared. But what can I replace y with? So come back over here. Be careful here. I can solve this for y and replace it with 1/3 x, right? Take that, plug that in here. Wouldn't you get 1/9 x squared when you square it? Yeah? Then over here, I could solve this for z. Z would be negative 1/3 x, wouldn't it?